Okay, so today we're looking at solving exponential equations. We're going to do this using logarithms. This is a fun skill. There's a few different ways we can work with it. So, solving exponential equations graphically. I like to start off by graphing the left-hand side, graph the right-hand side, solve the equation by finding the intersection. I'll come around, I want to see it on your graphing calculator. I'll pause the video a minute for this one. So we should be able to draw the graph quite quickly and easily. We add a page, we add a graph. We want the left-hand side, which is 275 times e to the 0.006x.
There's one zero.
Only 1 0. And then we want the right-hand side graphing of 1,000. We can see that this needs to go up to 1,000. We can adjust these ones. We want that one at 0. We want this one, make this one 30. We see the graphs intersect at this point. We press menu, analyze graph, intersection, and then we can find the intersection. Let me just get this value. Notice I've got 1,000 written here as 1 times 10 to the 3. Now, E means 10 to the power times 10 to the power. Sometimes if you just change your document settings, often I've got my document settings on float 3. It'll be clearer in float usually. All right, there's our solution. Noting this on the paper, so the question is asking you to draw it and graph it. So a method is required. On a graphical solution, the method is to sketch what you see on the calculator. This is y is equal to 1,000. You have to label the graphs. This is y is equal to 275 times e to the 0.06x. And this point of intersection is 21.5, 1,000. This is x, this is y. This is the method for a graphical solution. You've used your calculator, you found these values using the calculator. You would show it like this, but then you have to give your answer. This implies that x is equal to 21.5. Krista?
Because on mine we're not allowed a calculator.
Okay, let's move on. So we're going to have a look at solving this question algebraically. We're going to give an exact answer and an approximate solution. So our typical solution for these type of equations, there's a few ways we can go about it. The best thing to do is to simplify always to a to the x is equal to b. Aim for this equation. Aim for this equation, then we can solve it. You don't always quite get there, but you get to something looking like this. So starting off, we have 275 times e to the 0.06x is equal to 1,000. We need to divide both sides by 275. We get e to the 0.06x is equal to 1,000 over 275. Let's simplify that. Divide by 25 first. So this type of a simplification, you can see that 275 is a multiple of 25 quite quickly, and that's how you're going to get there. There's 4 25s and 100, 8 and 200, 8, 9, 10, 11. There's 4 and 100, so 4, 8, 12, 16, 20, 24, 28. How many are there in 1,000? 40. Excellent. So we get this. we need to take, so the new step that we're going to do is we can rearrange this. There's two steps here. We can rearrange it into by using the definition of the logarithm, or my preferred way is to take logs of both sides. So I'm going to take logs of both sides of the equation. It's going to look like this. Now, you can choose to take logs in any base. Typically, we would either take logs in common logs or natural logs. Which would be best here? Why? We do know the base is e. It would be best to take natural logs. If you have base e, take natural logarithms. So we take logarithms of both sides. It goes like this on the equation. On the left-hand side, we have e to the 0.06x. On the right-hand side, we have 40 over 11. Take logs of both sides. When you take logs of both sides, you take logs of everything. The entire, like we do with square root. You're taking a function, not like multiplication where you can multiply every term. Well, you can't actually multiply every term. You multiply the whole bracket, but then you've got the distributive property, which makes it look like you're multiplying every term. You're actually multiplying the whole side and then distributing. But you do that all in one step these days. What can we do with this 0.06x? If you've done the IXL homework on the properties of logarithms, you would know very easily what we would do with this. It is imperative that you do these homeworks before the next class, so I don't look to a room full of people who look dumb. The properties of logarithms, look them up on your formula sheet. It's on the Google Classroom. Look them up in your notebooks.
Power property, because 0.06 4 log natural.
Sorry, we have Carlos answering this question. Look, Carlos has done the homework, which is now he knows what he's talking about. He says we can use the power property. If we use the power property, we get 0.06x ln e is equal to ln 40 over 100. Thank you, Carlos. What is the natural logarithm of e? No. This must be memorized. What is the common logarithm of 10? Why?
The base is e.
Okay. If you have ln of e is equal to something, rearrange into exponent form, that means we've got e to the x is equal to e. What does x have to be? What is the natural logarithm of e? Again, we can look at this as, you can memorize this fact. This is really important to memorize this one. The natural logarithm of e is 1. The natural logarithm of 1 is 0. Memorize these ones. In fact, the logarithm of the base is 1. The logarithm in any base of the base is 1. The logarithm in any base of 1 is 0. Memorize these two facts. They make things much quicker for you, much easier. Also, we can look at this from another perspective. It's the inverse functions of each other. So the logarithm of e to the 1 is 1. you've got your inverse functions. You're taking the logarithm of e to the y. So e to the x and ln of x are inverse functions of each other. They cancel each other out. This means we have x is equal to ln of 40 over 11 divided by 0.06. This is the exact answer to this question. We can write this as ln 40 minus ln 11 over 0.06. Both of these two I would consider to be simplest possible form. I don't see either as being a simpler form than the other. I would consider both these to be simplest possible form. Just depending on how you're writing it, this can be nicer just to write it like this. This is also correct. Use your calculator now to enter this one of these two expressions and find the approximate answer to 3 decimal places. To 3 decimal places, we have 21.516. The same answer as we got in the last question. Same answer as we got in the last question.
So how about the 11?
To get ln on the calculator, you should watch me when I'm using the calculator here. The buttons go red to show you what I'm pressing. I'm pressing this. I'm pressing this. This is where ln is. Okay, have a go at this question for yourself. So this first one, we need to take away 2 from both sides. We get 2 e to the x minus 1 is equal to 75. Divide by 2, e to the x minus 1 is 42.5.
37.
37? 37.5, of course, yes. Take natural logarithms of both sides. X minus 1 is equal to ln 37.5. X is equal to ln 37.5. Now be careful with your minus 1 on this when we add 1 to this here. Just do it up here. If I add 1, it could look like it's inside, so why don't I just write it as x is equal to 1 plus ln 37.5. It's less ambiguous when we read it. And then approximate on your calculator. 1 plus ln 37.5. 4624. 4624. X approximately equals 4.624. Let's look at the second one. So we can rearrange this to be 3x is equal to log base 6 of 12. So x is equal to 1/3 log base 6 of 12. I can write, so this is simplest possible form. I can write it like this. Log base 6 of the cube root of 12. I want to write it as a single logarithm. Using the power property of logarithms, I can bring the exponent. I can bring it in as an exponent. We can write it like this. We can do a change of base on this if we want. So you need to have it in common logarithms. Let's do a change of base. We can do log base. Oh, let me do it into ln. Okay, let me change the base e. ln of the cube root of 12 over ln 6 using the change of base formula. This is the expression that you would have got had we just taken natural logarithms of both sides here at this point. we would get 3x is equal to 3x times ln6 is equal to ln12. And then we can rearrange this one to be 1/3 ln12 over ln6. And then we can get to that way as well. Multiple ways you go through the problem. When I ask for simplest possible form, I would be happy with any of these.
Sir, I don't get how you can reduce like 6 above with respect to here, just like 6 above.
This one to here,
I get that you're supposed to divide 6 on both sides.
I'm rearranging using the definition of the logarithm. So on the formula sheet,
Oh, I get it.
you can get your formula sheet here, formula booklet.
Oh, yeah, I get it actually.
Yeah. Let me just pull the formula sheet up anyway. It's on the Google Classroom. You want to be familiar with these ones. So we're going to use the exponent rules a little bit. Here are the logarithm rules. There's the change of base formula at the bottom. There. This is the power rule, the multiplication, the division rule, and this is the definition of the logarithm there, that top one.
So,
Yeah.
are you gonna have this on the money?
Yeah. Okay, so real world problem. Okay, so suppose that $250 is deposited into an account that pays 4.5% compounded quarterly. The equation is given here, where n is in quarters. Ooh. Okay. Solve for n. So let's get our equation. We've got a is equal to 250 times 1 plus r over 4. So we are going to be using 0.045 over 4 times n. So n is in quarters.
So is this exponential growth into here?
Yeah. So lesson 2. We need to solve this. How long it takes to have 500 in the account? Let me just see, is that formula on the formula sheet? No. All right, so what we can do first is we want to divide both sides by 250. That's going to give us 2 is equal to 1 plus 0.045 over 4 to the n. Take logs of both sides, and we should take, we don't want to be taking logs in this as our base now, do we? So we're much better off just taking logs. I'm going to use ln, so ln2 is equal to n times ln of 1 plus 0.045 over 4. It's annoying that we can't simplify that easily. What is that divided by 4? 45 does not divide by 4, I see. So that is 25. I'm going to simplify this expression a little bit. This is 1.01125 for this. Add these together, it's a bit neater. So n is equal to ln2 over ln 1.01125, which approximately, do we need an approximate? This is the exact value. Type that one into our calculator. We get 61.9.
So isn't it 62?
I'm just going to reread the question. So in the question, it says, suppose that 250 is deposited in an account. The equation gives the amount in the account after n quarters for the initial P. Solve for n to find how long it takes for the account to contain at least 500. So it's never going to have 500 in the account. It's compounded quarterly. So on the 62nd quarter, we'll have a little bit more than 500 in the account. On the 61st quarter, we'll have less in the account. It isn't compounded continuously, so it's only adding interest once every quarter. So in the 3 months between those two, it will stay at the same rate as it is at 61. This implies that n is equal to 62. This is 62 quarters.
So isn't it greater than equal to inequality?
No. In the question, we're asked to find a value of n so that the account has at least 500. So after 62 quarters, it will have at least. How long it will take? It will take 62. So let's say I ask you, how long will it take you to walk home? And you're like, okay, it takes me 40 minutes to walk home. Does that mean it can take you 3 hours or 100 hours to walk home? You would express it as the first given amount. Have I got this one for yourself? So if we have, do we need to even know what the initial investment is on this question?
Yeah.
Why?
So that happens for the triple double.
Oh,
Don't you end up with 3 equals? You would never need it, because if you want the initial investment to triple, you got 3 times whatever that is. There's the initial investment. You've got 1 plus 1 plus 0.045 over 4. If we wanted to do it in quarters, we'll just raise it to the n, like this. Divide both sides by the initial amount. 3 is equal to 1.011, was it 25? Yeah. To the n. Take logs of both sides. So ln3 is equal to n times ln 1.01125. N is equal to ln3 over ln 1.01125.
That's basically my work.
That's the exact answer to this one, the exact value.
Sorry, I didn't quite understand why you do one add 0.04.
That's the actual
That's kind of how you calculate a compound growth rate. So if we wanted to, let me just do a quick bit on this. Insert page after. Oh, sorry.
So if we wanted to increase something, we have X and we wanted to increase it by 20%, we can times it by this. This would increase it. If we wanted to increase it by 20% every year for X number of years, this would be, N number of years, this would be the sort of formula. So we're increasing by 20%, that means we've got X, which is 1 plus 0.02 to the N. We could write this as X is 1 plus 20% to the N. We could write it as X is 1 plus 20 over 100 to the N. Typically where these type of formulas come from.
Do you have to write 1 plus, or you could just write like 1
Well, if it's 20%, you could go straight to this. I'd be happy with that. Know where you're coming from on that one. But sometimes if you've got to adjust it for quarters, for a quarterly sort of interest rate or a monthly interest rate, got to divide it by 12 or something, then typically we set it up more like this. Normally I would set up the general model for compound interest as future value equals present value, 1 plus interest rate, which is in percent, over 100 times k raised to the k times t. So if time is in number of years, and so k would be, if it's quarters, 4. I would put in as 4.5 and then divide it by 100. This is your usual formula for compound interest. All right, that's it for today. Have a go at these IXLs. Make sure they're all finished by Wednesday morning.